All right, so I'm going to be teaching this class here. Sorry I cannot be in class today, just trying to get some visa stuff done. So you get to do a repeat of what we did in Pre-Calc 12, not too bad. So, and the nice thing is, what I'm doing today is essentially just a recap of what you learned last year, so this shouldn't be anything new. So with tension, tension is a common kind of question that we deal with when we're talking about two different objects. So two objects connected by a rope or a string or something that can be pulled but not pushed. You don't push anything with a rope. So the first kind of example here is an Atwood machine. So these are two masses that are suspended by a pulley. So what this would look like is I've got a pulley in the middle here, and I've got one mass hanging off of one end, another mass hanging off another end like this, and we need to deal with what's happening in this case. So for this, let's first draw the forces. So let's say this is mass 1, let's say this is mass 2. So the force of gravity on mass 1 is this way, force of gravity on mass 2 is this way, and then I've got tension applying upwards like this. So this is what this situation looks like. Depending on the masses will depend on what direction this flows. So if mass 1 is bigger, a larger value, mass 1 will go down, causing mass 2 to go up. So these two are connected by a rope. So it'll move together. If they don't, your rope is going to break. So we need to make sure that those move together. So like I said, FG is both downwards. They're both connected by the pulley. So those forces are going to work in opposition to each other. So F1 and F2, they're fighting over which one's going to win. Will work in opposition to each other. And whichever one's bigger, that one's going to accelerate. So the masses will accelerate so that the larger mass wins. Meaning the larger mass is going to go downwards. And since they're attached by the rope, the acceleration for both of these must be equal. So if they're not equal, if one accelerates faster, you're going to break the rope. So that's the Atwood machine. Note a few things here. So tension is a force that exists on a rope, and it acts the same as any other force. So it's just like a push or a pull, with two important things. So first of all, it's an internal force, meaning it acts in both directions in the middle of the rope. So if you've got a rope that's stretched across, at any point in here, it's going to act the same. So if I take my wire here, anywhere on this wire, there's an equal force pushing in either direction. So if I take a look at this specific point, tension's pulling this way, tension's pulling this way. Same with this point over here, pulling in both directions, as long as the rope is fully tight. So internal force acting in both directions. At any point in the rope. And the second thing when we're dealing with this is if I'm looking at the whole system, so looking at both masses, tension cancels out. So it cancels out of the F net equation. For the whole system. So if you want to solve for tension, you need to look at one object. You can't look at them both at the same time. So a few strategies in solving these. It's easy for us to choose the direction of the heavier mass winning. So take a look at the whole system and see what direction is moving. So the direction is positive in the direction of motion. So when solving these problems, it's easiest for us to choose the direction as positive in the direction of motion. So if I'm looking at this case that I'm dealing with over here, come on. So I'm dealing with this. If this object is moving downwards, the bigger force is down. So positive is down, negative's up. On the other side, positive is upwards because it's moving up, and negative is opposing that. So depending on the direction of motion, you pick positive as that case. So if I put some numbers here and say this is 5, this is 2, the bigger mass goes down. So I'm going to rotate counterclockwise, such as this. So if that's the case, this direction is positive, this direction is negative, because this object's moving down. Whereas this one is moving upwards, so up is going to be positive this side, and down is negative. So depending on the motion, positive changes direction. So just think of which direction is your object moving, and that dictates what's positive, what's negative. And also remember the acceleration of the two masses must be the same, or must be equal. If they're not equal, it doesn't work. I don't like this one. This one just says to expand it out to be a single line, but I don't like to do that, so just ignore it. If you want to give it a go, you're more than welcome to, but I think it's more confusing because then you have forces of gravity going sideways, which doesn't make sense. So let's do a problem. We've got two masses here that are on a frictionless pulley. So this is the Atwood machine. And we want to figure out their acceleration. So here's our situation. We'll say that this is 8 and this is 5. So we'll start off by drawing the forces on this. So we'll say this is FG1 and this is FG2. Notice I said that FG1 is bigger because it's a larger mass. The two tensions are going to be the same. You don't have to put the lines here to say they're the same. We're going to assume that. Tension's always the same on the same rope. And then let's go about solving it. So our strategy for this is the same as lots of other dynamics questions. We're going to first need what is the F net. So in this case, F net is, let's take all the positive forces. So this one is moving down, the 8 kilograms is moving down, so FG1 is positive. And our positive force on the other side is tension, because this object is moving up. So FG1 plus tension minus FG2 minus tension. So this is the overall system. So on this side, this is positive. On this side, up is positive. Again, just looking at the direction of motion. From here, we can actually solve this. I have the mass, so I can figure this out. We are looking for acceleration, right? Yeah, okay. So F net is ma equals mg. My two tensions cancel out of the equation, minus mg. The question is, which mass goes where? So you need to think about that. Which mass is which? So these ones are pretty easy. Fg1, I have to use mass 1. Fg2, I need to use mass 2. But if I'm looking at F net, I'm looking at the net force for this whole system. So if I'm looking for the F net for the whole system, I need what is the mass for the whole system. So this is the total mass. What is the total mass that I have in this situation? So as we go about solving this, let's take a look here. So now I can plug in numbers. My total mass, you can figure this out, is 8 plus 5. Just adding the two masses together. Then mass 1, we didn't figure out which one's mass. Oh no, I said this one's mass 1. And this is mass 2. So M1 is 8 times 9.8 minus mass 2, which is 5 times 9.8. And from here, you get acceleration equals a number. I actually have this calculated. So 2.26 meters per second squared. So this is my overall acceleration to get this. From here, I didn't ask it in this question, but from here, you can get the tension just by looking at one of these objects. So if I completely ignore this part, this doesn't work because you can still see it. If I completely ignore this part and just look at the 8 kilogram mass, from here I can make an F net equation. So I've got Fg1 minus tension equals this single mass times acceleration. So I can just deal with one mass to get tension. And this is something we said last year. If you want to solve for acceleration, look at the whole system. If you want the tension, look at just one mass. So note here, when calculating acceleration, we use total mass. And this is because we're looking at the F net for the whole system. So, not too bad. I already gave this away, but let's do this. So now we're actually going to solve for the tension in this case. So if we use the same free body diagrams and the equations as before, the two tension forces cancel. So I can't actually use that, and this is because it's an internal force. So as I already spoiled, we need to just use one of the masses. So if I quickly draw out the situation we have on the other page, this one was 8, this one's 5, right? That's what I did, yep. And if I redraw the forces, Fg1, tension, Fg2, tension, and now we want what is the tension. So we're just going to look at one. So if I do an F net equation for the 8 kilogram mass, so I get Fg1 minus tension, I could do this. So F net is M1A equals M1G minus tension. And you can see from here, I have everything. I can solve this. So M1 is 8. The acceleration we figured out on the other page, 2.26 equals 8 times 9.8 minus tension. And then just solve for tension. So here you'll get 60.3 newtons. If you did this for the other mass, it would give you the same answer. So if I quickly did this for the other one, so I'd have F net equals tension minus Fg2, and you plug in the number, so M2A equals T minus M2G. If you actually calculated this, you'd get the exact same answer. I'm not going to do it for the sake of time, but this would work. And the reason why this works is because the tension for both, for the rope is going to be the same. So either one is fine because both tensions are the same. Yeah, so the strategy for this, we only use one mass. I said this already. Just filling in the blanks so when you look back on your notes, you can understand this. So that is using the Atwood machine. The strategy for doing all the other versions is going to look the exact same. We want to look for the whole system, use the or if you want to solve for acceleration, use the whole system. If you want to solve for tension, use one of the masses. That's the strategy we're going to use for every single situation. So let's say I've got two blocks attached and shown like this, and we have friction. So my strategy for this is, what does it say? Solve for acceleration, solve for tension. Very common. So if I want to solve first for acceleration, we need the whole system. So let's draw out all the forces acting here. So I've got Fg, what did I call this one? I said this one's Fg2. I said this is Fg1. It doesn't matter which one you do, call 1 or 2. I just want to be consistent with my notes. I've got normal forces, so force normal 2, force normal 1. We've got a force applied here, so I'll just write this as force applied. I've got tension, so this is already drawn here. Tension, tension, these are the same. And we are told, what else? Coefficient of friction, so we have friction force. So I've got force of friction 2, because I called this the 2, and I've got force of friction 1. So you can see in our F net equation, we're going to have lots of forces. However, that's not going to freak us out when we actually solve this, because we can still do it pretty easily. So let's make our F net equation. So when we're doing F net, we need to think, what are the positive forces? So in this case, we're going to move to the right, because that's the force applied. So anything moving in this direction must be positive. Anything going the other way must be negative. So our positive forces are going to be force applied plus tension. Force applied, tension. Those are the only ones going to the right. Up and down, we don't care about those. Those cancel out. And then we have everything going in the negative direction. So minus tension, minus force of friction 1, minus force of friction 2. Okay, so that's going to be the overall equation for this. Tensions cancel, thankfully. And then now we need to solve this. So F net, this is the mass total, because we're looking at the whole system, equals force applied, because that value we're going to be given, minus force of friction 1. So remember, force of friction is just mu times the normal force. The normal force is equal to Fg, and Fg is equal to mg. Let me just show that up here. So force of friction is equal to mu Fn. Right? In this case, Fn is equal to Fg. So mu equals Fg, and Fg equals mg. So I'm essentially just restating that. So for force of friction 1, I've got mu m1g minus mu m2g. Sorry, this is a bit crowded. So mu m2g. And then from here, you just plug in numbers. So total mass, we've got 8 plus 6 times the acceleration. Force applied is given as 75 minus, you've got mu, you've got m1. I'm not going to plug in all the numbers into this. For those of you who want to write it all out, you can. I'm just going to save space and get A equals 2.9 meters per second squared. Again, just for the sake of time. So this is our acceleration. This goes on and on and on. You can plug in the numbers if you want. If you have any questions on that, come see me in class and I can show you what it actually looks like. So this is our total acceleration. That's part A. If I want to solve for tension, I need to look at just one of these objects. Again, it doesn't matter which one you pick. Either one will get you the same answer, so you can do whichever one you want. I'm going to pick mass 1. There's just less forces, so it's a little bit easier. So with this one, we've got F net equals tension minus force of friction 1. So we got M1A equals tension minus mu M1G. And again, I have the mass, I have the acceleration, I have all these values. So I can go ahead and solve for this and get that T is equal to 42.8 newtons. Again, if you have the space, you can put in the numbers and actually solve it. But this is what you get. So that's the tension. If you use the other mass, you'd get the same thing. You can just, it'll still be the same thing. Okay, last one. The one where you've got a mass that is hanging off of the edge. Like this. We're going to do the exact same thing. Solving for acceleration, use the whole system. Solving for tension, use one of the masses. So let's draw out what our forces are in this case. So let's say this one's mass 1. So here's Fg1. Here's tension. Here's tension. I've got Fg2. And I've got normal force. And nothing's mentioned about friction, thank goodness. So mu equals 0, we have no friction. If we did have friction, not very hard, put a friction force. But we don't need to. So then let's make an F net equation. F net equals all the positive forces minus the negative. So my positive force, Fg1, minus tension plus tension. And the tensions cancel. Positive tension, negative tension, because we're moving in this direction. So this is the positive direction. So my mass total times acceleration is simply equal to mass 1 times the acceleration due to gravity. So now we can just plug in the numbers and solve it. So total mass, 8 plus 6, times our acceleration equals mass 1, which is 6, times 9.8, and acceleration, plug in the numbers, you get 4.2. So that is my acceleration for this. Notice, an interesting fact with this, it doesn't matter how big this object is. If this is 20 million kilograms and this is 1 gram, this is still going to move. Because look at this, there's no opposing force. So as long as this mass is not 0, you're going to accelerate. It might be really slow, but even if it's 1 gram and 2 million grams, 2 million kilograms, whatever I said, it's still going to accelerate. And that's because there's no friction. There's nothing to slow it down. Then let's solve for tension. So this one's going to be easier. There's only one force. But again, if you did this, wouldn't matter. So let's do F net for mass 2. This is simply equal to tension. So tension is going to equal mass 2 times the acceleration. You have acceleration, you have mass 2. So 8 times 4.2. And we get tension of 33.6 newtons. So there you go. That's the summary of tension. And this is what you learned last year. So in general, the strategy for this, when you're given a situation, first, draw the free body diagrams. Always put these in first. That gives you an indication as to what's happening in the question. Once you've made the free body diagram, depending on what you're solving for, if you're looking for acceleration, total F net equation. If you're looking for tension, one of the masses, and use the F net equation for that. Because generally with this, it's always going to be that pair, acceleration or tension. Those are the two things you're going to solve for. So that is a review of tension.